Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to another lecture on control systems. So today we shall be continuing with what we have been discussing thus far, in the sense that of course we shall be discussing a new tool today, at least we shall start discussing one today, but this new tool will also be in continuation with the other tool that we learned the other day, which was Bode plot, in the sense that both of them are frequency domain tools, and that is why quite opposed in nature to the root locus technique that we had learnt earlier. So what necessitates or motivates us to study this Nyquist criteria? Of course we mentioned that Bode plots are in some sense self-contained, that is, if you spend enough time on it you can actually design controllers of the same variety, that is lag compensators, lead compensators or lag lead compensators, independent of the root locus technique, right. We of course did not have time to delve too much into the depths of that, but we showed you a sketch, a rough sketch of how you can sort of go about designing compensators using Bode plots alone. Nonetheless, there is something a little disconcerting about Bode plots. Somewhere we get the feeling, and that is not just due to the fact that I have kind of glossed over those issues, but also at the fundamental level we feel a little less comfortable with Bode plots, particularly when the question of stability arises. You see, when we were talking about this root locus technique, we could see things pretty transparently, very clearly, right, because we could see the pole 0 locations and we could see how the closed loop poles sort of moved or shifted as you changed a parameter, that is the gain of the open loop system, right. Unfortunately, when we dealt with Bode plots, all we were dealing with were the open loop transfer function, yeah, and so this notion of this closed loop pole and its location and what translates to violation of the stability condition or whatever is this stability condition, these questions are left somewhat unanswered if we just deal with Bode plots. So that makes us a little uncomfortable, and therefore strongly motivates us towards studying this frequency domain technique called Nyquist criteria in a certain amount of detail, right. There is also another historical reason, and when I mention that you will actually realize it is related to something that I mentioned in the other class the other day. So you recall that when you have, for instance, a root locus, suppose some root locus branch, I mean I do not care where the other poles and zeros are, it could be anywhere, yeah, but suppose you have some root locus branch, maybe there are some other poles and zeros, yeah, never mind that, but suppose you have a root locus branch that goes like this and by symmetry like this, yeah. Now imagine that you have chosen a particular value of k such that your closed loop pole is here, right, yeah. Now it might be that you reduce this gain in the hope of improving stability, right, but on the contrary what this will do is it will take your closed loop pole closer to the j omega axis. So there could arise a situation where reducing the gain is detrimental to stability. Now this is something that early researchers or early engineers who are dealing just with frequency response through the lens of Bode plots found it hard to wrap their heads around. In fact, in the Bell labs, people were initially very surprised when they found that there do exist systems where not just increasing the gain leads to instability, but even decreasing the gain could sometimes lead to instability, right. And that made people uncomfortable, just like we might feel a little uncomfortable just knowing Bode plots without knowing the pole zero maps, yeah. So some people were uncomfortable, and that, as it turns out, motivated people to probe this question in a certain amount of detail. Now look, here in order to explain this, I have resorted to this root locus, and from this root locus you can clearly see that this situation is not totally unexpected, right. You can have a root locus branch which goes from the LHP back to the RHP and then comes back again to the LHP, yeah. So there are two crossovers here. Now this would, in the case of Bode plot, translate to multiple crossover frequencies, yeah. In fact, if you recall from our earlier discussion in the previous lecture, what we said was that this point where the closed loop system would have exactly purely imaginary poles, yeah, corresponded to the coinciding of the phase crossover and the gain crossover frequency, right. So if there are two particular frequencies at which there is phase crossover and gain crossover occurring at the same time, then obviously in the Bode plot also such situations can arise. Now unfortunately this does not appear as intuitive or as transparent as, say for instance, this picture here, this root locus picture here, right. So what I am trying to essentially say is that there seems to be something missing in our understanding, right, if we only look at the Bode plot. So I hope that with that in mind you will now appreciate that even if what we are going to study next, this Nyquist criteria that I have mentioned, might appear on the face of it to be a little more complicated than some of the tools we have studied earlier, it still does make sense to try and grasp this concept, because it helps us in seeing stability through the frequency domain, yeah, independent of any time domain technique such as root locus. So with that in mind, we will now study the Nyquist criteria, and to embark on this mission of studying the Nyquist criteria, we will have to understand something else. So if you will permit me or indulge me a little, yeah, I will actually digress a bit. I say digress, but it is not really a digression, as you shall realize hopefully by the end of today's lecture itself. But for the time being it might appear like I am talking about something completely uncorrelated to whatever we have discussed so far. It might seem like a complete journey into complex variables and plotting their roots and plotting different contours and stuff, right. But if you do bear with me for a while, at least for today's lecture, by the end of it I hope that you will be able to see that it all falls in place. These are like pieces in the puzzle that will help us in answering that stability question through the lens of the frequency domain alone, yeah. Okay, so with that in mind, let us now dive into this so called contour mapping. Okay, so what is a contour? I mean, if you feel that the term is like it's bogging you down, or you find it's a little too technical or complicated, let us just say it's a closed curve. Where is this closed curve being drawn? Well, you take the complex plane for instance, right, and let us say you draw a closed curve like this. So yeah, something like this. So this is a contour, yeah, simple, nothing too fancy or too complicated. Now recall that if you have a function in a complex variable, say fs, yeah, so fs is let us say a mapping from complex plane to the complex plane. So it picks out a value from the complex plane, its argument, this s comes from the complex plane, and then fs is also a complex number in the sense that every time you pass on a particular complex value, say s through f, what you get back is another complex number, it spits out another complex number which also has a real part and an imaginary part. So as we had earlier also explained this, you can now take this to be the real part of f and this to be the imaginary part of f, yeah. So for example, you pick out any point on this complex plane, this is the argand plane, this one is the argand plane here. So you take any point on the argand plane and you pass it through this, it will have an image, okay. So this is like the domain, yeah, and this is like the codomain of f. So this is the domain of f, this is the codomain of f. As I also mentioned earlier in another lecture, if you just had a real variable and a real valued function, you could have drawn both of them on the same curve. You could have just labeled the x axis to be the independent variable, that is the domain, and the y axis would actually stand for the codomain, right. So all possible values that it can take, yeah, a subset of that you will see in the on the y axis, yeah, that's called the range of values that it can take under the mapping f, yeah. Unfortunately, when you have complex numbers, they are themselves two dimensional, represented on a plane. Now you want to represent the mapping of a complex number through a function which also spits out a complex number. So remember, if this were a mapping from C to R, then you might have actually drawn another third axis here and you might have plotted that function. But unfortunately this is two dimensional, this is two dimensional, so you cannot really sketch it on the same curve even on a 3D plot. So that is why what we do is we take arguments from this argand plane, pass it through f and look at its image on another plane, which is also a complex plane, but its real axis, its x axis is just the real part of the fs, and the y axis is the imaginary part of fs, right. Now what we are doing when we are saying we are doing contour mapping is, instead of taking arbitrary values or arbitrary numbers from this complex plane, you see there are like, you can choose arbitrarily this point, that point here. When you have just this x and fx, yeah, the choice of what value to choose is not very difficult. You can just go along this straight line and you can choose x1, x2, yeah, and you will have, let us say, f of x1 something like this, let us say you have this as f of x2 something like this, right. So you can plot it on the same graph as I said, and you know exactly where to look for your domain, your members in the elements in the domain. But here, which way do you go? Do you pick a point here and then next point you pick arbitrarily here, then you pick here, then you pick here? I mean, it's random, it's arbitrary, right. So in order to get rid of this arbitrariness, we just map a contour instead of mapping any arbitrary sort of point or set of points here. Or you can say I am going to map this entire set, yeah, I am going to map every point in this set, I am going to look at its image here, yeah. So that also can be done. So here this contour mapping is a special type of mapping where we say that instead of looking for arbitrary points in our domain, we will trace our path along this contour, and we will pick our points. So we will call this S1, call this S2, call this S3, and obviously just like here we have discretized it, here also if you take these points S1, S2, S3 close enough, we will get a reasonable approximation of this here. Now the first observation that you can make is that if you take a closed contour here, you will also get a closed contour here. Why? Because quite simply, once you have made one round around this contour, you come back to the same point where you started from. So obviously if it is a single valued function, which is what it is, yeah, we assume it is a single valued function, then at this point say S1, it can have exactly one unique value. So you started with S1, say this is your point f of S1, and then you go here f of S2 for example, and you go back like this and you come back to this point f of S1, so it has to close here. So a contour on this path or on this domain will also lead to a contour on the codomain. One critical assumption we are going to make is that there are all these points that we choose on this contour, or the way we choose this contour is that f of S is so called analytic on the contour we choose, right. So in other words, at every point on this contour, around every point on this contour, yeah, in a neighborhood of that point you can expand f of S in a convergent series, yeah, that's what analyticity is, right. So f of S is analytic on the contour we choose. So we do not encounter points, nasty points, right, where they tend to blow up, where f of S tends to blow up. we avoid those points. If there are such points, then we maybe bypass those points, right. So that is what we do. So that will allow us to sort of plot this. The reason why we make this assumption is because if we encounter points where this fs is not analytic, we will not be able to evaluate fs and plot it here. So it's basically quite straightforward why we do this, okay. So we make the assumption that fs is analytic. So now why are we interested in this? Just sometimes it helps to keep your eyes on the main objective. The main objective is we were trying to study this stability question in frequency domain independent of our understanding of root locus, okay. So typically what sort of functions do we encounter? I mean, you can obviously consider any type of complex function and you can do a contour mapping of that, but that will not really be a question that bothers us at this point because we are concerned with a very particular kind of fs. In general, our fs, we will look at fs that is rational, yeah. So in our particular case, it makes sense to only look at rational functions, right. Why rational functions? Because recall all the functions that we are dealing with, yeah, they all come from transfer functions for us. So we are going to restrict our attention to not any arbitrary complex function that is analytic, yeah, you can have several of those. So within those analytic functions we will only look at those functions that are rational and analytic on the contour or at every point on the contour, okay. So we will only restrict ourselves to that, we will not go for any arbitrary sort of functions, let us say just polynomials, yeah, or exponentials or things like that, we will just look at rational functions. So what is the property of rational functions? We know that any rational function of s, you know, will look something like s minus z1, s minus z2 dot dot till s minus zm, yeah, it can be factored into linear factors like this, and s minus p1, s minus p2 dot dot till s minus pn, where of course z1, z2 dot dot till zm and p1, p2 dot dot till pn, they are all complex numbers, yeah, we allow them. So when we are allowing this linear factorization, we have to accept that some of them may be complex, the poles and zeros may be complex, they need not be real, but we do not care. I mean, so far as this factorization is concerned, here after all we are not looking to get the inverse Laplace transform and things like that. That is when we kept them, those conjugate roots together, because we wanted only real factors in some cases, right. But here we do not care, this is just an analytical tool, right, a tool for our analysis. So here we can factorize this polynomial in the numerator into linear factors, yeah, if we allow the complex factorization over complex numbers, and similarly the denominator can also be factorized into linear terms like we have done here. So this is typically the sort of terms or the sort of functions fs that we are going to focus on, and notice that if our contour that we choose does not pass through the points p1, p2 so on till pn, then that analyticity of the function will also be ensured. So we will not pass through, we will not choose our contour so that it passes through any of those so called poles of this function fs. Alright. So now having done that, where are we now with this, or how does this contour mapping actually help us? So consider, first we will take this block again like we did for the Bode plot, we will take this piece by piece. So let me take just this first piece here, and let us just look at this, yeah, this is R, this is JR, okay, and let us say this is where your Z1 is, and this is where my contour is. So let us call this contour as C, curly C if you like. So what are we going to do here? What we are going to do here is we are going to call this S1, call this point S2, call this point S3, yeah, and our Fs, for now we are just focusing on this blue term. So our Fs is just 1, just one 0, okay, no poles. I know this is a polynomial, you would say, but you talked about rationals, yeah, but remember in the Bode plot also we took this out piece by piece, yeah, we had a rational function but we took out individual blocks piece by piece, they were all polynomials themselves individually, right, or reciprocals of polynomials if they were in the poles, right. So here just bear with me. So first we are going to study each individual block, and just like we saw in case of Bode plot we can piece them together back again, here also we are going to do something similar, alright. So what is the objective of all of this? So now you see if you pass this through Fs, what is this map going to be like? Okay, so this is going to be real part of Fs and this is going to be imaginary part of Fs. So this is going to be actually pretty simple. So for example, you take this point S1 here, so what is, so this is S1, so what is this? This is, let us say, theta 1. So what is S1 minus Z1? Let us say this length you call as L1, yeah. So then this is nothing but the number, the magnitude L1, which is of course positive real number with an angle theta 1. This is the representation of that complex number S1 minus Z1, yeah, in the polar form. So if I now want to map this point here, what do I do? Well, I just measure off this angle theta 1, so I take this length L1 and I map it here. So I just draw this phasor of length L1, yeah, at an angle theta 1, and this is going to be my point f of S1, yeah, because remember this is nothing but f of S1. If you just substitute S1 instead of S in this function, yeah, that is what you get. So similarly you go to S2, then you have this other line, yeah. So let us say this line has a length L2, this has a line angle theta 2. So what I have to do is I have to now draw this second line here, yeah, like this, this is theta 2, this is of length L2, like this. So it really does not take too much imagination or a flight of fancy to see what is going on here, it is quite straightforward actually. All that is happening is this entire contour, you see, is getting shifted, yeah, it is as if this Z1 has moved to the origin, right, yeah. So what happens then is, if I were to draw this curve here, let me use a red one, of course I may not be able to replicate this exactly, but trust me this is exactly a replica of this curve. So let me try to, yeah, so this is going to be the map, yeah. So this contour I have drawn in black here maps to this contour I have drawn in red here, when your function Fs is just a 0, just a numerator, a linear factor in the numerator. So as it turns out, this one we really know what shape it has, what it looks like. The more critical question, which I have not really brought up thus far, at this point it might seem like I am only just interested in the shape of this, yeah, and we can say very nice things about the shape, it is just the same contour shifted, in this case a little to the left, yeah, right. So that seems to be the crux of this, but that is hardly the point here. The more important point here is, you see, the observation that if this Z1, yeah, this contour is outside this, I mean this point, sorry, this 0 is outside this contour. So if this point Z1 is outside this contour, then you take one trip around this contour and you map it here, what happens? You see, initially you go from S1 and like this, if you go and trace, so let me use the arrowhead key here. So if you go and trace your path in this direction in the, and that is what is important, the clockwise direction, okay. So it turns out if the contour C is traversed clockwise, then the mapped contour, which is the red one, the mapped contour, red one, yeah. So this is this red one, okay. So the mapped contour is also traversed clockwise, okay. Why is that so? Well, of course, it's kind of straightforward, it's staring you right in the face, it's the same contour as I said, right. So even this is traversed in the clockwise direction, because you see, you move around this, if this is moving clockwise, this is also moving clockwise. So from fs1 to fs2, if you go here, so this is, let us say, fs2, that also entails a clockwise movement. But the most important point, which is something I have not mentioned over here, is what is the net rotation of this red contour around the origin. In other words, if you traverse around this mapped contour, this mapped red contour here, yeah, you will see that if you look at this angle subtended, yeah, by any phasor on this. So initially it goes in this direction, the phase increases, and then it goes like this, yeah, and then it sort of again decreases, and then again increases and comes back. So the net rotation or the net phase change is 0. So the point to be taken home from is, and this is the more important point I would say, if Z1 is outside C, then the mapped, of course, red contour does not encircle the origin of the Fs plane. Which is the Fs plane? Of course, the Fs plane is the codomain. So this is the Fs plane, and that is quite obvious here. In this case, you can, as I said, this is a shape preserving sort of a mapping, right, because you are just considering a single factor here, okay, it is just a shift. But the point is that for every such 0 which is not inside this contour, the net phase change or the net change in angle or the net number of encirclements of the origin, yeah, in the clockwise or anti-clockwise direction is 0, okay. That is the take home message. So if I am making so much of an issue about it, I wonder if this point Z1 were inside this, would things have been different? Let us quickly check. So suppose now I have this Z1 the same here, and I choose a contour such as this, okay. So this is my Argand plane again, and let me see what the mapping will look like in the Fs plane, okay. Okay, so again let me choose these points S1, S2, S3 like this. So let me go about again in the clockwise sense, yeah. So remember that, and again this is a matter of taste, only that whatever we are going to deduce will change drastically in the sense that things will change, the convention will change, but as a matter of convention in this course, in this particular lecture, or for in fact for the purpose of this particular course, I shall always consider that this contour C. So let me just write that assumption. Contour C in the domain shall be considered to be traversed in the clockwise direction. Yeah. So that is our convention. You can, as a matter of fact, take an exercise and replicate whatever I am going to discuss today by choosing this contour C in the anti-clockwise direction. Yeah, you just try to figure out where things will change. It's just like an exercise, like you know what is root locus, try to figure out the rules for complementary root locus. It's something similar, same sort of a, not exactly the same question being studied there, but of course somehow creating some sort of an analogy. Yeah, you can take that as an exercise, but we shall assume throughout this course that whenever we are talking about Nyquist, this contour that we choose in the domain, in the Argand plane, is always going to be considered in the clockwise sense, and with that in mind, everything that we build from hereafter we will state. Yeah, so if you make this anti-clockwise, some of those statements will change. Now I leave it to you as an exercise to figure out which of them will change and how. Okay, but yeah, keep that in mind that we are always going to choose it clockwise. So in the same token, we first pass S1 through this, then S2, then S3, because we are traveling in the clockwise sense here. Okay, so let's take this for instance. Yeah, so this is our theta 1, this is L1 again. So we go here, and this is of course f of S1 here. Then we go here, which is f of S theta 2. So this is going to be f of S2. Similarly, you have here f of S3. So you will have f of S3. You see, the direction of traversal is still clockwise, right? We can still observe that the direction of traversal here is also clockwise. So it turns out that if you have a 0, a numerator factor here, whether the z, the 0 is inside the contour or it's outside the contour, the direction of traversal is always going to be clockwise if your original contour is in the clockwise sense. Yeah. So again, hereafter I will not always mention that the original contour is in the clockwise sense, because it's a standing assumption, as I said. Yeah, we will always choose this contour in the clockwise sense. Now, what then is the difference between these two cases? Yeah, this also apparently a clockwise contour maps to another clockwise contour. Here also a clockwise contour maps to another clockwise contour. Where would the difference arise, you might wonder, and that is where this question assumes significance. For instance, consider this point here, say S4. Okay, this is S4. What about S4 here? You see, our case here, this S4 will have an angle given by this minus theta 4, for instance. So here also we draw this minus theta 4, and this is our FS4. So if we keep drawing this, it turns out, of course, again the shape should be similar. It's my pathetic drawing that's making these two shapes appear different. But notice the key difference now. If this point Z1 lies inside the contour, yeah, then in the image space, in the codomain, the contour that you get here will now also be traversed clockwise like in the earlier case. Yeah, so if this is clockwise, this is also clockwise, but the one significant difference is that now the origin of the FS plane is being encircled once in the clockwise sense. Okay. So let me write that down. The difference between the first case and the second one is that although in either case the contour, that is the, okay, I have not drawn it in red, let me draw it in red here, yeah, that will help. Yeah, so this is the red, so the contour, the red one in the FS plane is traversed in the clockwise direction, of course under the assumption that the original contour in the Argand plane is also in the clockwise direction. Yet in the latter case, that is in the second case when Z1 is inside the contour that you have chosen, yet in the latter case what happens? The difference is the origin of the Fs plane is encircled, okay. Which does not happen in the former case, okay. So that is the important conclusion. So we have seen, if you map this simple piece, this simple factor S minus Z1, there are two possibilities. One where you have chosen the contour to include this point Z1 inside, that is the second case, and the other where this point Z1 lies outside the contour. In either case we have seen that the mapped contour, which is in red and drawn in the Fs plane, this mapped contour is always in the clockwise direction, but in the second case where you have included this Z1 inside the contour, the mapped contour does end up encircling the origin because there is a net phase change of 360 degrees as you go once around this path here, yeah, a net change of 360 degrees. You start from S1 and you come back to S1, look at these phasors L1, L2, L3, and as they change L4 and so on, yeah, this phasors, they keep rotating, yeah, if you follow this, they keep rotating like this, one full rotation 360 degrees, right. That is the significant difference. On the other hand, in the previous case where we had this, that the Z1 was outside the contour, you see that the entire rotation of the contour happened outside. So from a vantage point of Z1 which is outside this contour, you would only see a phasor rotating like this back and forth, yeah. So that if you start from the point S1 and you ended at the point S1, you will see that after some such oscillations or back and forth, the net phase change of that phasor, which is L, is 0. That is the significant difference, okay. Now having studied one of these factors, let us now study one of these other factors, that is these poles, yeah. So what is, I wonder, the effect of this pole here? Again we will have two cases, one where the contour does not include the pole inside, the other where the contour includes the pole inside, and we will see what sort of a difference it leads to, okay. So first consider that you have this pole here and that you have this contour here which is C, this is R, this is JR, okay, right. And again as before, choose this in clockwise sense. I mean this is kind of like going to be a convention, as I said, so we are not going to bother too much with it. So choose this as S1, this as S2, yeah, somewhat like this as S3. So these are our 3 points. So then I wonder what this corresponding mapping in the Fs plane is going to look like, okay. So let us see. So here, of course, in a moment it will be clear why I just drew a longer line here. You see here my Fs is going to be 1 by S minus P1, okay, or if you like similarity, let me write that with a green colored because I boxed it with a green thing, okay. So this is going to be S minus P1. Alright, so now we are mapping it through this here. So if you take this is going to be again of length L1 and this is going to be theta 1. When you map this number, what is its mapping going to be? This Fs1 is going to be 1 by L1, notice, yeah, with an angle minus theta 1. Why? Because this is sitting in the denominator. So now if this is theta 1, on this plot here, on this plane here, I have to actually draw minus theta 1, yeah, and if this is L1, then this is going to be 1 by L1. So if I consider this L1 to be smaller than 1, then this, okay, yeah, maybe I should draw a larger 1 by L1 here. So, this is of length 1 by L1. Yeah. Now, similarly, if you go for this L2 here, this is theta 2 here. So, again f of S2 here is going to be 1 by L2 with an angle minus theta 2. Now, notice that magnitude wise theta 2 is greater than theta 1, therefore, minus theta 2 would be somewhere further down here. So, if this point is your f of S1, where is your f of S2? Notice that f of S2 will be further rotated in the clockwise direction. Yeah. So, this being traversed in the clockwise direction also implies that this will be traversed in the clockwise direction as well, because remember minus theta 2 is going to be here, somewhere here. So, this is going to be minus theta 2. What about the length? Well, from this figure at least, again as I said, a lot was made about the shape, but that was because in case of a 0 it is very easy to see that the shape is just shifted, but here the shape is not preserved, and frankly I do not care about the shape. Yeah. Although in the earlier case I was talking about the shape, yeah, preserving the shape. If it looks like a kidney bean, the other should also look like a kidney bean. Here I do not care, because later on we will see when we use this Nyquist criteria, this will be inconsequential. All that we shall be bothered with is this total phase change, the total number of encirclements around the origin, which we have already got a clear picture about when studying the 0. Now we are going to try and do that same for the pole. So, how is this going to matter to us? Well, let us see. So, now notice this, from this figure it seems that L2 is greater than L1, therefore 1 by L1 is greater than 1 by L2. So, this 1 by L2 is going to be of a smaller length. So, probably something like this, yeah. So, in going from S1 to S2 you went in a clockwise sense, in going from Fs1 to Fs2, which is this, you are also going in a clockwise sense, yeah. So, if you allow me to sort of draw this, a rough approximation, when this line you see is going to be bigger. So, actually these points which are closer to this is say P1, the points which are closer to P1 here on this argand plane are going to map to distant points, are going to have longer lengths, the phases are going to have longer lengths here in the Fs plane. The points which are further off, they are going to be shorter. So, keeping that in mind, let me draw this in red then, some sort of an approximate contour here. Yeah. So, you see again as before, it seems like that every time you choose a clockwise contour in the argand plane, we are still ending up in the 3 cases we have studied so far. In each of these 3 cases, we get a clockwise contour in the Fs plane as well. The only difference being, of course, when the 0 was inside the contour, we had a full rotation or a full encirclement of the origin of the Fs plane. When the 0 was outside, we had no encirclement. Here also, if the pole is outside, yeah, you see the same thing happens to the phase change, the net phase change of S minus P1. So, if the net phase change of S minus P1 is 0 as you go once around this contour C, then the net phase change here is also going to be 0 as you study it from this origin here, yeah. So, it is not going to encircle the origin, that much I hope is clear. What about the last case that we are going to consider, which is when we have this same contour here, or rather, okay, let me draw a different contour, let me keep the pole like this, the same P1, and let me draw this sort of a contour like this. So, this is my contour C, this is R, this is J of R. And now I am going to again pass this through Fs, which is going to be 1 by S minus P1 as before, and I am going to try and draw this and see what this contour looks like in this case. Okay. So, let me take again as before some sample points to try and understand this. So, let us say this is S1, this is S2 and this is S3. Okay. All right, fantastic. So, we have first we have S1, so we have L1 with an angle theta 1, then we have S2 where we have L2 with an angle theta 2, and then we have L3, for S3 we have L3 with an angle, let us say minus theta 3. Okay. So, if I now map this here, notice that Fs1 is equal to 1 by L1 with an angle minus theta 1, Fs2 is an angle 1 by L2 with an angle minus theta 2, and Fs3 is a magnitude 1 by L3 with an angle plus theta 3, because I have chosen its angle itself conventionally here to be minus theta 3. Yeah. So, the sign gets reversed because it is in the reciprocal. Yeah. So, we know that the reciprocal of a complex number has the negative of the phase of the original complex number. So, now what can we say about this? Well, again as before we are going to traverse in the clockwise sense in the original contour in the Argand plane, and we are going to see how this changes here. Notice that first this is going to be theta 1. So, theta 1 is larger than theta 2. So, the magnitude, let me draw this point, this is minus theta 1 here, and now notice this point theta 2. What about this point theta 2? Well, this theta 2 is less. So, here we have our first difference. Okay. As you go clockwise from S1 to S2, you get this as your Fs1, but then f of S2, you see you have gone from S1 to S2 by traversing clockwise in the contour C. But if you want to plot now Fs2, you will have to draw it along the line minus theta 2, and minus theta 2 happens to be less in magnitude than minus theta 1, as is evident from this figure. Yeah. If you go clockwise like this theta 1 is greater in magnitude than theta 2, therefore minus theta 2 magnitude wise is less than minus theta 1. I do not really, again as I said, I do not really care about the shape and the phase, I mean shape and the size of this line L1, L2, L3. Yeah. For the moment I am going to push that to the back burner. Yeah. So, you see that in going from S1 to S2 you traverse clockwise along the contour C, but in going from Fs1 to Fs2 you are actually traversing in the counterclockwise, and this is the first time we are encountering such a discrepancy between the two. So, that is one change already we have seen. Now, I wonder, will there be a change similar to this, that is, what about the number of encirclements around the origin? Will that also change? Well, quite evidently and obviously it will change. Why am I saying quite evidently and obviously? Just cast your attention to this contour here. If you traverse once around the contour, forget about the fact that this Fs is the reciprocal of S minus P1. Yeah. If you think of the nature of this contour here and the nature of this contour here with respect to Z1, yeah, you see that this nature is the same. In going around this contour C starting from the point P1, you see that this phasor traverses one complete 360 degrees in the clockwise direction, just like in the earlier case this contour, when you are traversing this contour C here, yeah, the phasor starting at Z1 and going on having its endpoints at different points on the contour, yeah, that also traversed complete 360 degrees once around, which essentially led to this encirclement of the origin. By the same token, here also we will end up with a similar situation. The only difference being that now this contour will be traversed in the anti-clockwise or counter-clockwise direction. Okay. So, that is going to be our only difference. Yeah. Other than that, insofar as the pole and 0 lying inside the contour is concerned, in both cases the origin will be encircled. Yeah. It is just about matter of simple drawing of complex numbers, no phasors. Yeah. You see, for example, if you want to convince yourself, you choose a point somewhere around here. Yeah. You choose a point somewhere around here or a point somewhere around here. So, why do you think this point is going to be having its map here? This point is going to have its map somewhere here, because this is going to be its angle, and if you draw its negative angle here, this is going to be its angle here. So, this is a point which is, let us say, some f of S5 maybe. Yeah. So this is going to be a point which is going to be mapping S5. So if you choose your let us say S4 here, then this point is probably going to be f of S4. Yeah. So you will see that this is exactly how it happens, right. As you go clockwise once around this, you will see that the origin of the Fs plane is encircled counterclockwise once, if you have a pole inside the contour. So this is all well and good, you might say, and we are actually beating about the bush, it seems. As I said, do bear with me a while and we will start to see the benefits of this sort of an analysis, or this understanding that we are gaining now through this contour mapping. So you might say, very reasonably I would say that, well, you have just taken one piece at a time. So you have just taken one pole, one zero and one pole and seen the effect. So what is going to be the effect of multiple of those fellows being present at the same time? Yeah, can you say anything about it? Well, so let us try. So let me take two scenarios again. In one case I have a pole and a zero like this, and in the other case I have the locations of the poles and the zeros interchanged. So let us take this as R and this is JR, this is R and this is JR. So this is, let us say, P1, this is Z1, this is Z1, this is P1. Of course you will be able to identify these two as no, sorry, forget about that, these are all in RHP. I do not really care in this case. So don't, I was actually thinking we will identify them with lag lead compensators, but no, forget about it. Let us not give any control theoretic notation to this at the moment. Just look at them as rational functions, right. And let us say we consider our contour like this in either case. Yeah. Why am I including both of them inside? You see, if I do not include both of them inside, if I were to draw a contour like this, say some contour like this here and some contour like this here, it is boring, because I know that once I traverse around this contour, one full circle, one full rotation if I go around this contour here, the net contribution due to S minus P1 or 1 by S minus P1 is going to be 0, the net contribution due to S minus Z1 is also going to be 0, here also the same thing, so it is boring. But now I want to see what is going to happen if I have both of these fellows inside, what is going to be the net contribution. So f of S is going to be S minus Z1 by S minus P1, here also S minus Z1 upon S minus P1, and let us see the effect of this. This is my R, this is my, sorry, not R, JR, this is going to be my real part of Fs, real part of F and the imaginary part of F. Here also, yeah, we are mapping here. Here also we have the real part of F and the imaginary part of F, right. Okay. So let us see. So let us choose sample points here. This is, say, S1 and we traverse a little clockwise S2 and then we go S3. Here also let me mark out S1, S2, S3. So what is going to be this function here? Let me call this length of this line as L11 and this is, say, L12, right. So then this function f of S1 is going to be, and let us say this is theta 1, theta Z1 and this is theta P1, okay, right. So then this is going to be nothing but according to that map over there, L11 upon L12 with an angle theta Z1 minus theta P1. Now notice that from this geometry of this figure here, this angle theta P1 is the exterior angle which is the sum of the interior opposite angles. So therefore theta P1 is greater than theta Z1, therefore this net angle is negative here. So I will end up with a point somewhere over here once again, as I said, I don't really care about this L11 and L12 relative magnitudes, it's just the phase that I am concerned with, yeah. So this is going to be a point somewhere here Fs1. Now let's go to S2, okay. What happens at S2? Of course, at S2 also the angle theta P2 is greater than the angle theta Z2, yeah. So this angle, so Fs2 is going to be, let us say, L21 upon L22 with an angle theta Z2 minus theta P2. So again this theta Z2 minus theta P2 is going to be still a negative angle, but what is its direction of rotation going to be? What is its, is it going to increase from this or decrease from this? You see, in order to understand that, just go here, yeah, at this point, alright. And here you see that here at this point, if you go slightly ahead of S3, you will have 0. So that means you are basically approaching this point 0 at some point, no? So basically this causes a rotation, or let me draw this in red here. So this essentially causes a rotation like this in the counterclockwise direction, yeah. And notice that there will be no encirclement of the origin. Why am I claiming there will be no encirclement about the origin? This is very critical to understand, okay. The reason I am saying there will be no encirclement about the origin is that you note, if you go around this at every point here, yeah, like this, you will see that what is going to be the role played by this angle here. You come to a point here, for instance, yeah. Now you see that you have a positive angle, yeah. This is going to be theta, let us call this point S4. So this is going to be theta P4 or minus theta P4, because this is a negative angle, and this is going to be minus theta Z4. So the angle is going to be theta P4 minus theta Z4, which is going to be a positive angle, so it is going to be somewhere here, right. But notice that when you go somewhere here, around here, yeah, and around this entire thing, unlike in the earlier case where you had just one pole and one zero, yeah, in this case if you go around like this, around this whole contour here, yeah, at no point, yeah, the claim I am making here is that at no point will you see that this phase will go around this origin. So at no point does this contour ever go once around this origin, okay. And so there is actually the question of this encirclement doesn't even arise in this case, right. So in order to see this more transparently, just see what is this difference in angle after all. You concentrate on this figure here, you see this is the external angle and this is the sum of interior opposite angles. So the difference between these angles, that is the pole and the zero, this is something similar to what we did for this phase lag lead compensators, right. So this is the net phase contributed, you see. Now if this angle has to be 180 degrees, yeah, which is what is necessary for a crossing on the negative real axis, yeah, then this contour must go through this. So let me redraw that here. Suppose you've been really nasty in choosing this this contour, okay. So suppose you've chosen a contour somewhere like this, okay, let me take that. So it's a pole and a zero. So you have a pole here and a zero here, and suppose you've chosen a contour like this to include both of them, right. But notice, even then you will have 2 points at which potentially, see at this point it is 0 because both of them subtend 180 degrees, at this point it is again 0 because both of them subtend 0. So at the only points where this 180 degree crossing can happen in the real f and the imaginary f, yeah, in this plane. So this is the Argand plane and this is the Argand plane and this is the functions plane, right, fs plane. So in this part, if you want to cross this point somewhere here on the negative real axis, then you must necessarily have a contour here which passes through like this. But notice that this contour must have an even number of crossings between this pole and 0, yeah, because otherwise one of these fellows will be left out of this closed path, correct. There is no way you can have an odd number of crossings between this pole and 0 of this contour and yet have both of them inside the contour. right. So this even number of such cuttings means that even if you manage to cross, yeah, right after that you will actually cross back again. So if you geometrically also, if you look at this figure, this point is free, it is not encircled, okay. So for example, you will have something like this and something like this. So therefore this point is not really encircled, right. So that is why you see, no matter how you draw with this 1 pole 1 0 scenario, it will never cross. Now by the similar argument, you can try that out as an exercise. If you just interchange the position of the pole and the 0, the arguments all remain the same except for one crucial little change, and the crucial little change will be that it will, of course I do not know about the shape, so the shape will not be preserved between these two, but the only crucial difference insofar as the traversal is concerned is that this will now go clockwise, yeah. You can just apply the exact same reasoning as we applied earlier and you will see that this will go clockwise once around it, but nonetheless even in this case, in the worst case what might happen is again something similar to this. So you have some pole 0 configuration like this, and if you have been really nasty about your choice of contour, you might have chosen some bad contour like this to really make things nasty, but yet you will see that the worst that can happen in such a scenario is that you will again have some crossing over like this, something like this, right. It will not be anything worse than this. So this point, this origin will still not be encircled by the corresponding contour in this FS plane, right. So that is the important observation. Of course all this is under the assumption that we have a single pole and a single 0 inside this. In the next lecture we shall see the more general case when we have n number of poles and m number of zeros inside a contour, and we will see how those contours look, or if they encircle the origin, then how they do so or how many times they do so, right. So we will see a geometric interpretation of that. So until then, take care, thank you.